Dear students, welcome back. In the previous lecture, we had seen linear homogeneous ordinary differential equations. In this lecture, so the previous lecture was lecture 28. Okay, lecture 28. And so today I'm going to combine two lectures and give it as one lecture, only with the purpose that I don't want to break the lecture. Otherwise, whatever the content we cover today is a material of two lectures. So we are going to see lecture 29 and 30 together in this lecture, which is why. So this is the lecture which is corresponding to 16th June and 18th June, right? So two lectures corresponding to that. So in the previous lecture, what we had seen is when you have a linear kth order differential equation where this ak were constants, they are functions independent, so they are constant functions independent of the x variable. Sorry, this should be I di dx I. Okay, so what we have seen is solutions to this ODE. So in this lecture, what we are going to look at is how to solve non-homogeneous linear kth order differential equations. Okay, so when you have f0, we have dealt in the previous lecture. In this lecture, we are going to look at the situation when you may have a non-zero functions here. So this is the linear non-homogeneous situation. Oh man, what is this? What's happening? Okay, so we have a linear non-homogeneous. We have a linear non-homogeneous kth order ODE. So you have Ly equal to f in this form. Okay, so the idea is this. See, you have a linear operator. We have already said this is linear, right? And you have f, what we have already seen. So you can think of L, right? We have already seen that this L is actually a map from the space of continuous the vector space of continuous functions to the vector space of continuous functions, right? Where the domain is actually, if it's a kth order, the proper domain is ck, right? So I have already explained in my previous lecture that you can think of vector space as set. So this is, suppose you say this is ck of I bar set, and if you have c of I bar set, then this mapping L is, this differential map is this, right? So when we say, so in the previous lecture, when we solved for the homogeneous situation, when we said you wanted to solve Ly equal to 0, so 0 is some element in, right, in the space of continuous functions. So 0, suppose 0 is here, what you are looking for is this inverse image, right? Is this inverse image of z. So that set here, so ideally I should not draw it like this, because usually it is set, so it will be a subspace, and we said that is, so if you recall, we had introduced the notation NL, the null space is the set of all y such that Ly is 0. So this null space is some set like this. So you can think of the null space. So here you see I'm drawing, pictorially I'm drawing a two-dimensional image, but you know that we have seen theorem that this NL is actually a k-dimensional subset, right? And it has to, because it's a subspace, it has to pass through the zero vector of this set. Okay, so anyway, so point is there is a, so let me just to distinguish will it work? No, auto work. So anyway, so you have a solution space for this ODE, which is the null space, and which was, so the inverse image of this point 0. So when you say this, the inverse image of this point 0 was this set, what you have here, right? This set. Now we are going to ask this question. We don't have, we take any f, some f here. What is the inverse image of that under L, under the same operator L inverse? So what you have done, since this is a vector space, you see that what you have done, what you are asking is more or less, when you have translated f, when you are translated from the origin to f, what happens to this, right? The idea is that if you can, so let me, okay, so let me understand. So we have, so now we are asking this question, what happens to Ly equal to f, where f is a non-zero element. So what is the corresponding so what is the corresponding set here which is mapped to f, right? Now and the good thing about is that we can actually relate that set with this null space of L. So the way we can see is that, recall that if you want to solve this, you start with f, you can think of f as f plus 0, right? And you look at the same operator L, so you look at if you know, so f, you can think of this as f of Ly, right? Or in other words, right, f of Ly, so all y such that Ly is 0, which is precisely the zero element. But you know what is this? This is in the, and similarly, if you know at least one solution, let's say you know an yp, so let's call this as yc, right? So that is, this is any, yc is any element in the null space of L, right? And you know that's a k-dimensional set. So yc is any random element in null space of L, and if you know one yp such that Lyp, if you know one, so we want to find all y such that Ly is equal to f. Suppose you know there is one, suppose you are able to find one y such that Ly equal to f, so let's call that yp. Then this is Ly, Lyc, but L is linear, so this is same as Ly plus p, yp plus yc. So if you want to find all y such that Ly is f, it's actually yp plus null space of L, because any yc is an element of null space. So the general solution for all, so any y, so any y should come from this set, right? So what I'm saying is that to solve, so the solution to this problem is any y which is coming from yp plus null space of L, where yp is any one solution of this equation. So basically, if you want to solve this ODE, it's enough to find one solution which satisfies this equation. Let's call it yp, and then you translate that. Then you translate the null space with that solution, and every element of this set is a solution to this ODE. Okay, this is from the vector space structure, right? That's what I've said here. So for 0, you had null space. So for when you take any point f, its corresponding set is, you translate this set with y plus null space. So it's some set like this. Okay, that is how. So that's the idea. So that is how we are going to solve a linear non-homogeneous equation. So that's what this theorem is stating here. Whatever I have just explained here is the theorem that is stating here. So if you want to solve Ly equal to f, you find one particular solution, one particular integral. Okay, one solution such that Lyp is equal to f. So we want to find all such solutions, but if yp is one such solution of the non-homogeneous ODE, that is this ODE, then yc plus yp, yp is this, right? Yc is the, so yp is the one solution. Then yc plus p, what is yc? Yc is the solution corresponding, is in the, yc is an element of the homogeneous equation. So yc is in the null space of L. So for all element in the null space of L, you just sum this. That is the general solution of the non-homogeneous ODE. So there is a name attached, so which is why we have used the subscript yc, yp. For particular integral, you call yp, which is the one solution of Ly equal to, and yc is the complementary, yc is, c denotes the complementary function. Okay, so the name attached to that. So if you take, so that, what is the idea? How do you solve Ly equal to f? What is this theorem telling you? You first solve for Ly equal to 0, right? You know how to do it from previous lecture. So then you have a null space of L, which is the set of all solutions to the homogeneous equation. Now using this homogeneous equation, so any element here is called yc. Yc is any element in null space, which is the general solution corresponding to the homogeneous equation. Right? And then you find at least one solution of the non-homogeneous, right? Once you find one solution, you can find all solutions by doing yc plus yc, yp plus yc, where yc is from the null space. That's this theorem telling you. Okay, when we see examples, you will understand better. So I have given this proof of this theorem as an assignment because it's easy. I've already explained pictorially in this lecture whatever is the proof of this theorem. So please try doing it. I've given it as a problem in the assignment sheet. Okay. So, but the idea is this, that you take any element of the null space, that is, which is the general solution of the homogeneous equation Ly equal to 0. We have seen in the previous lecture, which involves arbitrary constants, and to that you add one particular integral, particular solution, and that is your general solution. Okay, that's how you solve a non-homogeneous ODE of the same form. Okay, let's look at examples. So you see, this is, in the previous lectures we have solved this equation when it was homogeneous. If you recall, we had shown that this is a second order ODE. So sine and cos are the linearly independent solution. So the general solution is the linear combination of sine and cos. We have seen this in the previous lecture. Now we have a non-homogeneous ODE, that is an X here. Okay. So what is the idea? What is the theorem telling you? What is the algorithm to solve this? First you look at the corresponding homogeneous equation, which is this, right? So its complementary function is the solution of the corresponding homogeneous equation, which is the linear combination of sine and cos. So this is your the null space. So the corresponding so you forget this, look at the homogeneous equation and its general solution. Now you have to find, if you find one solution of this ODE, you just have to add it to it. So we will see later in the lecture how to find this one solution, but suppose we are able to find some means. For instance, in this case, you can guess that the function x is itself, because x double prime plus x will be equal to x, right? Because x double prime is 1, 0 plus x, which is x. Okay. So x itself is a solution. So x is one particular solution of this. You add that to the complementary function, that is the general solution of the homogeneous equation, then you get your general solution for the non-homogeneous ODE. So it is just sum of yc and yp. Okay, that's the idea. So just again to give you, so we just recall the algorithm here. So you have the general solution of the, so we have already, so whatever we have seen in the previous theorem is that the general solution of the kth order ODE, kth order linear non-homogeneous ODE is nothing but the sum of the general solution of the corresponding homogeneous equation and a particular integral of the non-homogeneous equation. Okay. So therefore, to solve an equation of the form Ly equal to f, it is enough to find, so there are two steps. One is you solve this homogeneous equation and you find one solution for the non-homogeneous equation. These are the two steps involved. In the previous lecture, we have already seen how to find these Ly equal to, how to find the null space, right, which will be of k dimension for a kth order linear homogeneous ODE. So finally what is left is how to find this one solution. Like in the previous example, we had guessed that x is the particular integral, right? In the previous example we had guessed it. Now so how do we find in the general case? Can we find at least one particular integral for any linear non-homogeneous ODE? Okay, and that is where the method of undetermined coefficients comes into play. That method tells you how to find the particular integral, but not for all cases, for some special cases of f. So when the right hand side f is of some special form, then you can use the method of undetermined coefficient, not special. When I say special form, of some particular cases, you can use a method of undetermined coefficients to find the particular integral, which means you can find the general solution of such problems. And what are the special of f that we will see that we can solve is, one is the polynomials, then is the exponential function, and then trigonometric polynomials. Okay, these are the three types, and any pointwise product or linear combination of these types can be done, because you are working with a linearity structure, right? And you can also work with pointwise product using compositions and so on. We are going to look at examples, then you will understand better. So basically the idea, what we are conveying in this slide is that if you want to solve Ly equal to f, solve for Ly equal to 0 and find one yp such that Lyp equal to f. And how to do this? For this you use the method of undetermined coefficients, and that method works not for any generic f but for special f of the following forms that we have mentioned here. Other cases you don't know yet how to do it, okay? But the theory that we have explained in the previous slides is valid for any f, because that is just using the vector space structure of this of the set of all continuous functions, okay? But this method of undetermined coefficients is very specific to this, but you'll understand better when we see examples and other things. The first thing is, how do I solve this? So what did we say? I want to find one solution yp such that Lyp equal to f, or in general, let's say we want to solve for Ly equal to f, which is the non-homogeneous equation, okay? So for the non-homogeneous equation is what we want to solve this way. So the idea is, suppose I can find a differential operator, right? Let's call it A. Suppose I find a differential operator A. So f is given to you already, L is given to you, because L is the differential equation, which means all the coefficients are given, which means you know what you don't know is y, right? F is given and L is given. So now you look for a differential operator, right? When I say differential operator, I mean look for a differential equation such that if I apply the differential equation, apply the derivatives on f, it's 0. For instance, in the previous cases, if you remember, when we did Ly equal to 0, L is given, right? 0 is anyway known, y is unknown. So what you are asking is, given L, what are the y such that it is mapped to 0? Here we are looking at the opposite in this case. In this case we are saying f is given, find the differential operator A such that it's 0. Okay, we will look at this case, which is why the condition on f comes in, right? We said we will do only special cases of f, because this is the reason why we look at special case of f, because for all f we may not be able to do this. It may not be easy to find this A, but for some f it's probably easy to find this A. So what is annihilator of a function? Annihilator basically means annihilates, right? It kills, right? So what is annihilator of a function? What is the differential operator which maps f to 0? That is annihilator of a function, okay? So why are we looking at annihilator? Suppose we find such such that AF is equal to 0. Then what we do in this differential equation is that you operate A both sides. Then what you get is A of Ly is A of f. But A was chosen such that AF is 0. So this right hand side becomes 0. So what you have is a new differential equation, which is A composition L of y equal to 0. So now what we have done by choosing this A is that we have changed, we have converted a non-homogeneous ODE to a homogeneous ODE. And if we solve for this ODE, then we have solved for this ODE, right? That is the idea of this annihilator. So you given f, you look for the differential operator such that AF is 0, use that f, using that you can change the ODE to a homogeneous ODE, and if you can solve this homogeneous ODE, you have solved this non-homogeneous ODE, okay? Okay, so I am using the word non-homogeneous in the sense of the thing. Usually the antonym of homogeneous is inhomogeneous, right? Inhomogeneous is the opposite of homogeneous. but in mathematics we use it interchangeably. So in this, you can also call it inhomogeneous. So when I say non-homogeneous, I basically mean that this f that you have here is a non-zero function. Okay, so that's the idea. So what is the annihilator of a function? Annihilator of a function is any differential map such that AF is 0. Okay, so just to simplify things, we introduced this symbol d power k as the kth derivative with respect to the independent variable. Okay, in this case I have used x to denote the independent variable, but it could be any symbol. So dk is the kth derivative of any function with respect to the independent variable. So now let's give an example. So suppose your f is e power mx. In this case, it is easy to find the differential operator a such that a e power mx is 0, right? What is the differential operators which you can find such that e power mx is 0? Simple is choose a to be d minus m. What is d? D power 1, that is d by dx minus m. This is your a. This acting on e power mx is always 0, right? You can verify that, right? Because derivative of e power mx will give you m e power mx minus m e power mx 0. So this is your a. The annihilator of e power mx. So for this function, it's easy to find a, right? You can have more than one. Like suppose I apply another differential operator. Since it's already 0, if I apply another d of a, so d of a is also, so there is no unique choice of a. You can have more than one choice of a. Choose the a which is simple for you, right? Choose the way which is easy for you to work for, right? So choose an a which is easy for you to work with the differential equation and so on. Okay, so this a, so no one is saying this. So this annihilator is unique. That is not always the case. You can have more than one annihilator, which is fine, right? One function can sit in the null space of different operators. That is possible. That's fine. So choose the one that is easy for you to find or easy to apply to your problem and so on, right? So for e power mx, d minus m, so whatever is the power m here, that comes here. So d minus m is the annihilator. So this form of f can be handled when you have a non-homogeneous ODE. This form of m can be handled. Now what about a polynomial x power n? Its annihilator is dn plus 1. You know that if I differentiate it n times, you will get a constant function. If you differentiate it n plus 1 time, you are going to get 0. So this is 0. So the annihilator is dn plus 1. So this is another class of function where you can find the annihilator, which is why we had special cases of f in the previous slide, right? For some class of functions like this, it is easy to find the annihilator. Now what about trigonometric polynomials? If you have sine ax plus b form, then the annihilator is d square plus a square, right? So d square plus a square acting on sine ax plus b is always 0. Similarly for cos, right? So similarly for cosine. So these are examples of cases of f where you can find the annihilator easily. Okay, and I have already motivated why we are looking at annihilators. Now you can also use this information. For instance, in this case, it is the product of these two cases, right? This is the product of these two cases. F is x and x. In this case, what is the annihilator? It is the composition of these two, right? So e power mx is d minus m, and x power n is the derivative of n plus 1. So the composition of these two is d minus m power n plus 1. So you can actually verify that this acting on this f will give you 0. So this is your annihilator A. Okay, so similarly, though we have given you 3 examples here, you can also consider pointwise products of these types and so on. You can also consider linear combinations of these types. Okay, all this you can use. Okay, so this, I'm just saying that if you product functions, then the annihilator composes. So it's a composition of the annihilators. Okay. For instance, here again it's a product of the trigonometric polynomial and the polynomial. So here you already have seen that for sine it is d square plus a square. For x power n it is n plus 1. So this is the annihilator for this. Similarly, same annihilator works for x power n and cosine and so on. Okay, so when you have pointwise product, you can compose the annihilators. This is again an example of pointwise product of exponential and trigonometric polynomial. For trigonometric polynomial, it was d square plus a square, and when you compose it with exponential EMX, the d becomes d minus m. So you have d minus m square plus a square. Similar thing for this. So product by exponential gives a translation in the differential operator, right? This is something which, so for exponential, the d is d minus m, and for sine it's d square plus a square. So when you compose them, you actually have d minus m whole square plus a square. Okay. This is again, three products: the polynomial, exponential, and the trigonometric polynomial. So you compose three things. So sine gives you d square plus a square, exponential gives you d minus m square plus a square, the polynomial gives you power n minus 1. So that is the annihilator for this. So you can see, you can even do some complicated work. So all these types of f can be handled when it appears in the non-homogeneous case of a linear ordinary differential equation. Okay, so let's look at so if you recall, what was that we wanted to do? We wanted to look at a method such that you can find the particular integral corresponding to an f, right? And we have, and how do we do this? As I said, find a such that AF is 0, and then you have AL, then you solve this differential equation, and whatever the solution will be a solution to this problem. Okay, so given an inhomogeneous ODE, Ly equal to f, right? If f admits an annihilator A, that is AF equal to 0, then you have the new differential equation, but it's homogeneous. But now, of course, the order will increase, right? Because L is already of some k order, A will come with some order, right? So the A composed L will be k plus something, right? So it will be higher order, which is fine as long as we can solve it. So let's illustrate this for a second order situation, just as an example. For instance, if you are given a second order ODE, linear, so this L is your second order linear ODE, then your L is of this form. So Ly equal to f. Now if A is the annihilator of f, then the new homogeneous ODE that you get is A composed with L, which is this, right? And you need to solve for this homogeneous ODE. So therefore, the y that is obtained is a linear combination of linear independent solutions of this operator, right? That's how we have seen, right? For a homogeneous equation, the solution set, the dimension of the solution set of a homogeneous equation is the order of this operator. In this case, the order is 2 plus the order of A. So the solution that you will get will be linear combination of that many linearly independent solution, which is the order of this differential equation. Okay, so let's see how do we solve. So suppose I have a linear second order ODE where the right hand side is exponential, right? So what do? We have already seen, so we have to first find the annihilator of f, right? So what is the annihilator of f, which is e power mx? We have already seen that the annihilator is d minus m for emx. So d minus m of this operator, you get 0 because d minus m of this becomes 0. D minus m of emx is 0. So you have the homogeneous constant coefficient ODE. So you started with a constant coefficient. So all that we are doing in this lecture is for linear kth order constant coefficient non-homogeneous differential equation. Okay. Okay. So the variable coefficient is a issue that we will take up in the next lecture. So okay, so in this lecture it's all constant coefficient, but only thing is you have a inhomogeneous term on the right hand side, right? A non-zero term on the right hand side. So we have converted that to now a homogeneous constant coefficient, and this you know how to solve. We have already seen in the previous lecture how to solve an homogeneous equation of constant coefficient linear. So for this equation, there is a corresponding characteristic equation, which is of this form, right? That is what we have seen in the previous lecture, right? And in this case, you will see this is second order. So this is actually a kind of cubic equation. It will have 3 roots, right? So 2 roots from this quadratic equation. There will be 2 roots. Let's call it m1, m2, and then an additional root m coming from here. So there will be 3 roots. So you started with the second order ODE, but using annihilator, because of the form of f here, you ended up with a third order differential equation, and the corresponding characteristic equation admits 3 roots. Now you know, we have already seen theorem depending on repeated roots, distinct real roots, complex roots, and so on, how to solve it, right? So if the m that you obtain here, if the m that you obtain here is distinct from m1 and m2, which comes as solution of this, then yc plus yp is a solution, where yc is the solution to this second order ODE, and yp is something that we will, some scalar multiplied by e power mx, which is what we started with. It is not because of this, it's actually because of the fact that m is the distinct root, and you know that if m is one of the root, then the solution is of the form e power mx, but it's some linear, so some scalar multiple, right? And that a is what we need to find, which is why this is called the method of undetermined coefficient, right? So you have 3 roots, and we know for a homogeneous equation, if you have 3 roots, it is linear combination of, if you recall from the previous lecture, it's linear combination of m1 e power m1x, e power m2x, and the third root is m, so e power mx. So it's a linear combination because it's 3, so this is a linear combination of these 3 if these 3 are linearly independent. And for these 3 to be linearly independent, m1, m2, m should be distinct, and that's what I'm saying here. If one of them is same, then you accordingly you have a linearly independent choice here. You have an x here. You have a linearly independent choice here because this m is equal to either m1 or m2. That means e power mx is already taken. So you choose a linearly independent choice, which is x e power mx. So you multiply a scalar to that, and this is a is what you need to determine. Similarly, other cases, right? You have to do this for each case depending on if there is a linearly dependent solution that is appearing, then you choose an appropriate linearly independent situation. Now, if we obtain this a in y, in yp, if we compute this a, then we have solved for the general solution, because the general solution is yc plus yp, yc is already known, which is coming from these, and yp is what you need to find, and if you find a, you have found yp, so you have found the general solution, then you have solved the original problem. Okay, that's the idea. You will understand better when we show it via examples. So let's take this example. It's a second order ODE where your f is 2 e power 4x. Okay, so what you do, you look for the annihilator of your f. This is an exponential function, so the annihilator is 2 times d minus 4. We write is e power 4x, so d minus 4. So if you use this annihilator in this ODE both sides, then you get a homogeneous ODE of this form. But now this is a third order linear constant coefficient ODE. Okay. So if you look at the roots of the corresponding characteristic equation of this constant coefficient ODE, you will see there are 3 roots, right? So 4 is the root from here, and this second order ODE will give you 3 and minus 1. Okay, so you have these 3 roots, 3, minus 1 and 4, and these are all distinct roots, right? So what is your general solution? Your general solution is the linear combination of these 3 roots, that is alpha 1 times e power 3x, alpha 2 times e power minus x, and alpha 3 times e power 4x, right? Alpha 1, alpha 2 is generic as a general solution. What you need to find is just this alpha 3, which is the undetermined coefficient. So from this, you know that this should be a solution. So you use this information. So you use this information here. Use this y in here, right? If you use this, you already know that yc is the solution of this second order ODE here. So that will anyway kill this. So what will remain? So you see, if I replace y with this, I have replaced y with this, right? So if we replace y with this, what you will get is that this will anyway kill this term and so on. So this ODE here that you have here becomes this ODE. Sorry, I mean, I say this, I don't mean this, I mean this. If I use this y in this ODE, then I get this. Okay, but you already know that d square minus 2d, this acting on yc, because yc is actually the solution of this second order thing, homogeneous. So that is 0. So what you are left with is just this acting on the second term. Okay, so we have this. So you use this derivative. So you have the second derivative, this first derivative acting on this. Alpha 3 is what you need to find. Everything else is fine. So you differentiate, equate both sides, right? Equate coefficients of x or exponential of something. Then you should be able to get alpha 3. So if you differentiate it, you see you get, because there is a 4 here, if you differentiate twice, you get 4 square. So 16 minus 8 minus 3, alpha 3 e power 4x and 2 e power x. So this equation becomes this equation, and this e power 4x cancels with e power 4x here. What you're left with is alpha 3 is 2 over division of this, which is 5, right? 16 minus 8 is 8, 8 minus 3 is 5. So alpha 3 is 2 over 5. So you have found alpha 3. So you have found alpha 3. So since you have found alpha 3 here, your general solution of the inhomogeneous equation is yc plus 2 over 5 exponential 4x. So this is your general solution. So it's a second order equation. You have only 2 arbitrary constants. Okay. Now let's look at other examples. So you have a second order ODE. Your f is this exponential function. You look at the annihilator of this exponential function, which you know is d minus 3, so with a 2. So the annihilator is 2 of d minus 3. So you get this homogeneous equation. Now you look at the corresponding characteristic equation, which is now a cubic equation with roots 3 minus 1. So 3 is the root coming from here, and then 3 and minus 1 comes from here, right? These are roots, but here you see the one root of this coincides with one root of this, so there is a repeated root here, right? So from this, you know, you have to choose 3 linearly, because it's a third order equation. You need to choose 3 linear. This is a third order, so you should choose 3 linear. One is e power 3x from one root, another is e power minus 3x, the other is also giving you 3, so you should choose x e power 3x. It should be linear combination of that. So alpha 1, alpha 2, alpha 3 here, and this alpha 3 is the undetermined coefficient that you need to find. So that's what I'm saying here. So alpha 3 x e power 3x, where yc is the solution of this equation. Okay, so when you have repeated roots, this is what you do. Earlier we did not do this x. Now we have chosen this x because there is a repeated root here. Okay, so if you use this y, this is the y that you want to find, and this is the y that you want. So if you find alpha 3, you have the y. So you use that information in the given ODE. So your ODE becomes this. Now as again, d square acting on this yc, because yc is the solution of the second order ODE, so that will be 0. So you are only left with the second term. So you use this. So now you apply this derivative on this function, right? Alpha 3 is what you need to compute. So you differentiate. So you differentiate this on this function. So you will get an equation of this form, right? Because if you d square of, so you have to apply product rule, x e power 3x, right? So if you differentiate it once, you get x. So you have alpha 3 is of course there outside, forget that. So if you derivative, the first d square of this acting on ex will becomes so 3x e power 3x plus e power 3x. Yeah, that's it, 1. So this is the d part. Now you do d square part and so on, and if you apply this differential operator on this function, you will get this equation. And there, if you equate, in fact in this case you can quickly observe that there is a 9x coming from here, there is a 9x coming from here, so there will be no x term here. What will be left is just 6 minus 2, which is 4. So 2 by 4 is 1 by 2. So alpha 3 is 1 by 2. So there is a 6, 3, 2, 6 minus 2, 4. So 2 by 4 will appear here, which is 1 by 2. So alpha 3 is half. So if you use the information alpha 3 is half, you get yp is this, and your general solution is this. So it's right. So I hope you have understood how to do this, right? It's easy to do. Okay. Okay, let's look at another situation, another example. So in this case, you see we have f, which is a pointwise product of polynomial and exponential. So far we have been seeing only exponential, right? In that sense. So it's a second order equation. So you look at the annihilator of this, and what did we say is the annihilator of this? It should be the composition of this. So for x square, the annihilator is d cube, and for e power x, the annihilator is d minus 1, right? So it should be d minus 1 cube. So the annihilator is d minus 1 cube. So you have the new homogeneous equation, So what are the roots here? So you see 1, so this is already cubic, sorry, this is already quadratic here, and there's a cubic here, so it's actually fifth order equation, which is natural because you have a differential annihilator which is of third order, and then you have a second order, so that is going to give you a fifth order ODE. So this is actually a fifth order ODE. And what are the roots here? There's already 1 here which is repeated thrice, so there are 3 roots of 1 here, and then the roots of this quadratic equation which are 1 and 2, right? So you have 1, 2, and then 3 repeated roots of 1 from here. So you actually have 4 roots 1. So 3 roots of 1 here and 1, 1 here. Okay. And then there is a root 2. So what is the, so this is a fifth order equation. So what is the, so the solution space is actually generated by 5 linearly independent function. What are these 5 linearly independent function? One is of course e power x, and then e power 2x, then it should be e power x 3 times, but e power x already there, so it's x e power x, x square e power x, and x cube e power x, right? That's a linearly independent choice. So now you have 5 linearly independent functions. Okay, so that's what I have said here. So you have yc which has e power x and e power 2x, then you have x e power x, x square e power x, x cube e power x. So here the undetermined coefficients are alpha 3, alpha 4 and alpha 5. These are the 3 things which we need to find. Alpha 3, alpha 4, alpha 5 is what we need to determine. So the undetermined coefficients are 3 ones, alpha 3, alpha 4 and alpha 5. Okay. So you use the same technique that we have used before. So use this y in the original differential equation that you started with, which is here, right? Then you will immediately see that you have this acting on, this is what you will get, right? Because this is already making, so this acting on yc becomes 0, so what you're left with is this. Now you apply this differential operator on this function, you will have some terms, and then you have some terms here, equate the coefficients. Okay, so if you do all that, you will see that you will get that from the, so by equating one coefficient you will get some relation between alpha 3, alpha 4 and alpha 5. So this is one relation, this is second relation, and then this is third relation. The first relation gives you that alpha 5 is minus 1 over 3, and using that information here you will get alpha 4 is minus 1, and using alpha 4 you get the information that alpha 3 is minus 2. Okay, so you have computed all the 3 coefficients, alpha 3, alpha 4 and alpha 5. Use that information and you get your general solution to be this. Okay, so this way we have solved this equation. So you see the technique, right? The idea is you find the annihilator, use the annihilator to rewrite the ODE in the homogeneous form, and then you solve the way you solve a homogeneous constant coefficient ODE. So this is another example that I wanted to show where there is now product of x square e power x. Okay, in fact it's the same f here. What I have changed here is the coefficient here, and the, so here it's minus 3 and 2, whereas here it is minus. So what I've changed is the differential operator, okay, to just to kind of illustrate another situation. So as we always do, look for the annihilator, which is d minus 1 cube. So you have a second degree here and a third degree here, so it's a 5/5 degree ODE of constant coefficients. So what are the roots? So you already have 3 ones coming from here, So the roots are, and then this one, okay. So it's a fifth order equation. So you have 5 1. So 3 ones coming from here, 2 ones coming from this. So you have 5. So you have 5 roots, which are repeated roots 1. Okay. So you should have e power x, but 5. So now you do x e power x, right? X square e power x, x cube e power x, 1 2 3 4 5. So this is the choice. So these are the linearly independent functions that you should choose. So that's what we have done here. Okay. Now once you have this, use this y in this ODE. Okay. Then you get this ODE. Now you apply the derivatives for these functions. Okay. You will get some relations between alpha 3, alpha 4, alpha 5, and from here by equating the corresponding coefficients. So you have alpha 5 is 1 over 12 and alpha 3 and alpha 4 to be 0. So alpha 3 and alpha 4 are 0. What remains is only this. So your general solution is this. Okay. Okay, so that is about what we have seen so far. So let's look at the other situations. So let's look at more examples. So from here, I'm actually starting the lecture 30, the next lecture, which we are supposed to do on 18th June. I just don't want to break the lectures. I'm doing it in one video so that the content is available in one video, whereas the time or the material covered is for 2 lectures. So from this slide, it is the second lecture material, right? I mean the continuation of the previous lecture. So in this case, so we have seen the examples for when we had exponential, right? Now we are looking at the situation where we are doing trigonometric polynomials, right? We have also seen exponential. We have also seen some polynomials. So we'll just mix these examples, right? So this is the case where we have trigonometric polynomial sine on the right hand side for a second order ODE. And what is the annihilator for sine? We have already seen it's d square plus m square. So you use that equation. So now you get a fourth order constant coefficient ODE, right? So how do you solve it? You look for the roots. So you will have some roots m1 and m2 from this ODE, and then you have this complex roots plus or minus im from this ODE, right? Mu square plus m square. So you have 2 roots and 2 conjugate pair of complex roots. Sorry, 1 conjugate pair of complex roots. So if the complex roots are distinct from the roots that you obtain from this equation, then you just do the usual stuff, right? It is a fourth order equation. It is spanned by four linearly independent function, which is precisely those coming from this and the sine and cos coming from the complex roots, where this a and b are the coefficients that you would have to determine. Okay, so this is the undetermined coefficient in this case, right? And if the complex roots are equal to mi's, right, because there are 2 roots here and there are 2 roots here, if they become equal, then you choose a linearly independent yp. So you just add this x, you just multiply by x here, which we did not have here, right? And then we still have to find a and b. Right. Similarly, for each case, depending on whether you have repeated roots or repeated complex roots and so on, you have to choose accordingly, as we have done in the previous case, how we do for a homogeneous constant coefficient. Finally, you do that, you can use that information in the original equation y, and then you can use it to compute a and b, as we have seen in the previous examples, after equating like variables both sides. Let's look at an example. So this is now a linear combination of exponential and sine. Okay, so how do you, so in these cases, see, you remember when we did, what did we do? What should we supposed to do? We are supposed to look at the annihilator of this function together. No, we don't have to, because it's a linear operator. You can look at the separate annihilators and still that works, right? Because in this case the f is a linear combination of this and this, right? So and the annihilator of this e power x is different and the annihilator of sine is different, but that's okay, because for instance, you see, suppose Ly1 is equal to 2 power x, right, where L is this operator, whatever is given here. This, suppose this is your Ly, right? So if Ly1 is this and Ly2 is minus 10 sine of x, then you see by the linearity of Ly1 plus y2 is 2 e power x minus 10 sine x, right? So which means if you want to find the solution y here, you can independently solve this and solve this, and the solutions are just sum of these, right? You can write it like that. So we can actually think of, we can just use the annihilator of this separately, we can use the annihilator of this separately, right? We don't have to, so we can actually, so this equation you can think of as, if you want to, for instance, if I use the annihilator of this here, if I use the annihilator of this one, so what I will get is sum a1 composed with L of y1 is equal to 0, and then I'll get sum a2, which is the annihilator of, say, this, composed with L of y2 is 0. So then if I sum them, what I get is a composed with ly1, a1 composed with ly1, and a1 composed with a2 composed with ly2 is 0, right? Which is something similar to this. So we can actually use separate annihilators and then combine them. Okay. So what we are going to, we are going to show it, of course, via examples. So the corresponding corresponding characteristic equation of this ODE is the this polynomial, second degree quadratic equation, which has roots m1 and m, that is 3 and minus 1. So it has the general solution, this. Okay. Now the roots of the complementary equation, which is 3 and minus 1, whereas what is the annihilator of 2 power ex, which is 2d minus 1, and the annihilator of minus 10 sine x is minus 10d square minus 1, and that is this will give you one root, which is m3 equal to 1, and this will give you a pair of complex roots, right, which is plus or minus 1. Now, and these roots are distinct from 3 and minus 1. So you have 3 minus 1, 1 plus I and minus I, right? So these are the roots that we have. Okay, so using these functions, so the functions appear in F is a linear combination. E power x and sine x are linearly independent from the solutions of the homogeneous equation. That is, there is no repeated, so there is no roots matching them, right? For instance, what I am saying is that what is corresponding to m1 and m2, what you get is e power 3x and e power x. These do not appear in f. The e power 3x and e power minus x is linearly independent from e power x and sin x. So you are in, there is no linear dependence between the data and the solution that you are getting. So your particular integral can be written as like the way we did always, is y3 e power x, which is coming from these roots. m3 gives you e power x, and this complex pair of roots gives you alpha 4 sin x, alpha 5 sin x, right? Imaginary and the real part is 0, imaginary part is 1. So this is what you have, yp. So we need to find alpha 3, alpha 4, alpha 5, which are the undetermined coefficients. So if we use this in the differential equation here, right, if we use this in the differential equation here, then we get whatever equation that we have here, a relation between alpha 3, alpha 4, alpha 5. Okay, after we have applying all the derivatives and so on, we have used this yp in this equation in this, right, which is same as using yc plus yp in this equation, because whatever is this, if whatever is the differential operator here, if this acting on yc will make it 0, so find its equivalent to this differential operator acting on yp. That's what we have here. Okay, now you equate coefficients here. You have a coefficient of exponential x, you have a coefficient of sin x here, you have coefficient of sin x here, you have coefficient of cos x, you have coefficient of exponential x. So 2 is equal to minus 4 alpha 3, which gives you that alpha 3 is minus half. Similarly, alpha 4 plus 2 alpha 5 is minus 10, and minus 4, this coefficient is 0, this is minus 10, and what you have, this is 2, right? Equate that. So then you get this information that alpha is minus half, alpha 4 is 2, and alpha 5 is minus 1. So we have determined the coefficient. So your general solution is the linear combination of these. Okay, so alpha 1, alpha 2 coming from the original characteristic equation, and this is coming from what we computed, the undetermined coefficients. So that's the general solution of the given ODE, which is a constant coefficient non-homogeneous ODE. Now the same problem, let's look with some initial value. So we have already computed this general solution. In addition, if you have two conditions, because the second order equation you need two conditions, which is y0. So in this thing, you put x equal to 0, and you differentiate this y to get y prime, and put x equal to 0 and match this, then you can compute these constants alpha 1 and alpha 2. Okay, that's what we are doing here. So we have already seen that this is the general solution from the previous slide, and use the first initial condition. We get alpha 1 plus alpha 2, minus half minus 1 is 2, and if we differentiate the solution here, and we get the derivative to be this. Now here you put x equal to 0 and use this information that y prime of 0 is 4, so 4 equal to something, right? Where put x equal to 0 everywhere, you get another relation between alpha 1 and alpha 2. So you get this relation. So you have two unknowns, two equations, use them to solve. So if you simplify them, you get two equations in two unknowns. To solve for alpha 1, alpha 2, then you have the unique solution to the initial value problem. Okay, so that is how we have solved the initial value problem. So I think now we have done enough examples for you to understand the method of undetermined coefficients. So we will now do the last case, which is the case where the f is a polynomial, right? It's a polynomial now. So if you have a ODE where your f is any degree polynomial f, then you look at its annihilator, which we have seen is dk plus 1, right? So you apply that. So now you have a constant coefficient homogeneous ODE, but the order is k plus 3. So it should have k plus 3 roots. What are the k plus 3 roots? Roots m1 and m2 coming from here, and then k plus 1 repeated roots, which is a 0. 0 is the k plus 1 repeated root, assuming m1 and m2 are not 0. If one of the m1 and m2 is also 0, then the multiplicity of 0 increases. So now, depending on whether if both mi's are non-zero, then you have exactly k plus 1 repeated roots of 0. So then you have the general solution where yc is the solution corresponding to the second order type, which is corresponding to this m1 m2, right? It is e power m1x, e power m2x, and then this is the solution corresponding to 0, because when you say m equal to 0, it is e power 0x, which is 1, right? So now you have k plus 1. So you need to choose k plus 1 linearly independent solution. So you already have C m1, m2. m1, m2 is going to give you e m1x and e m2x. That is what is observed in the YC already, alpha 1 plus alpha. So linear combination of this is observed there. Whereas this 1 gives you, sorry, this 0, this m equal to 0, this m equal to 0 gives you e power 0x, which is 1. And how many such k plus? So you should have k plus 1. So you cannot have k plus 1. So you start with 1. You take x power 1, x square. These are all linearly independent. You need up to k plus. You need total k plus 1. So this is already, you go up to k. That's what I've done here. Okay. So it's a linear combination of this, and these coefficients ai are what we need to determine. Okay, so to obtain ai's in this, you use this y that we have here in this ODE that we started with, and this will kill the yc term, and what will remain is this acting on yp only. So use that information there, and then you can compute, you can determine the unknown coefficients ai's. If one of the m1 m2 is 0, then you need to choose your yp with another multiple x, because already there will be 1 there, so you have to start here with an x. Okay, so that is one. And the fact that one of the mi is 0 means that a0 is 0. If both the mi's are 0, that means a1, a2 is 0, then you are just left with the second derivative operator, so you can just integrate and solve them. So, but the same method will also work. Okay, so but the equation gets simplified in the case when the roots of the second order ODE becomes 0. Okay, so let's look at examples. You have a fourth order ODE where the right hand side is a linear combination of a polynomial and sine and cosine, right? So what you do, you look at the characteristic equation of this, which is m square plus 4, which is a fourth order, which is a fourth degree polynomial. So you have 4 roots, that is 2 0 repeated roots, and a pair of conjugate complex roots, right? So the general solution is you have 2 repeated roots, which gives you alpha 1 plus alpha 2, 2 repeated 0 roots, and then the complex roots gives you a linear combination. So this is the general solution corresponding to the homogeneous equation coming from this. Now we use the annihilators of these functions individually, right? And if we use them, so 3x square has the annihilator t cube, which has 3 0 roots. So already there are 2 repeated 0 from here, and there is 1, and then there are 3 0 roots coming from here. Okay, so that 3 0 roots, and there are already 2 here, so 1x is taken. You start with x square, x cube, x power 4. Okay, coming from these 3 0 roots. Now what about 4 sin x? The 4 sin x and minus 2 cos x has the annihilator d square plus 1, which has the complex root plus or minus I, which means the corresponding solution is, so real part is 0, so exponential 0, so it's a linear combination of sine and cos. But linear combination of sine and cos is already appearing here in the complementary function, so you need to choose a linearly independent choice from this. So you do with a multiple of x, so linear combination of sine and cos with multiplied by x. Okay, so your yp is this and this, so your yp is sum of this and this, so you have 1 to a b c d e, so you have 5 coefficients which are undetermined coefficients. This is the yp that you need to find. So the idea is to use this yp in the equation. So if you use it in the ODE, you get this relation. Now if you match the equate like variables, I mean coefficients here and there of x square, sine and cos, then you get the relation between the a, b, c, d, e. So you can solve for a, b, c, d, e, which you will get a to be, if you do the computation, you can see that a is 1/4, b is 0, c is -3, d is 1 and e is 2. Okay, after equating the coefficients, right? So what I am saying here is that you see, for instance, like you club in all the, for instance, these are all constant terms, which here it's 0, so that sum will give you 0. All the sine terms here can be clubbed to match it with this sine term. All the cos terms here should be clubbed to match it with the cos term here, and all the x squared terms here should be matched with here. So the x squared term you can already see here. 12ax squared should be equal to 3, which means a is 3 by 12, which is 1/4. That's how you get this. And 6bx, there is no x term here, which means 6b is 0, so you get b equal to 0. Okay, and so on. And since a is already 1/4, so this is already 1/6, and then with this you should equate it to 0, so you should get this, and so on. So you can compute this. Okay, so once you compute this, you have the general solution. Okay, now let's look at another example. This is again a linear combination of x squared exponential x e power x e power 3x. Okay, now in this case, if you look at the characteristic equation corresponding to this thing, then you get 2 roots 1 and 2, which gives you the complementary function. Okay, which is a linear combination of e power x and e power 2x. Now the reason why I am giving this example is that you see, now if you look at the annihilator of x square, which is fine. If you look at the annihilator of annihilator of e power x and x e power x, they have the roots 1, which is same as the root 1 here. So they don't have a linearly independent connections, right? These annihilators have the same roots as here. So now we need to choose a linearly independent set here. So for instance, what I'm saying is that e power x is coming here, but e power x is also coming from here. There's one root there. So you need to choose a linearly independent equation, right? So how do you do this? So if you look at this, so what is the annihilator of this? Annihilator of this is d cube, right? So this has 0 roots with multiplicity 3, and that gives you 1 x squared, right? E power 0 is 1, so 1 x squared. So this gives you this term. So the 2x square, so that if you look at the annihilator of 2x square, that gives you these 3 terms. Then if you look at the annihilator of these, they have the roots as 1, right? We have already seen this is d minus 1, which is 1, but 1 is already appearing here. You already have used 1 e power x here. So now you have multiplicity 2 here, right? So you use x e power x and x square e power x. So these 2 terms here gives you these 2 terms here, and this last term here, there is no e power 3x, so this is fine. This is coming from this because the root of that is 3, and 3 is what you are getting here. Okay, so the annihilator here will give you the root 3. 3 is not here, it's a distinct root, so 3 will give you this. So now you have 6 coefficients to compute. So you use this information in this ODE and match the coefficients. Then you see, so you'll get 2ax square is equal to 2, which gives you a is 1. Okay, and 2f is equal to 4, which gives you f equal to 2. Okay, and here minus 2e will give you 2, which is giving you e is minus 1. And if you use e is minus 1 information and match this 2, you get d is minus 3, right? And if you use these information back again here, since you have found we're matching this, there is no x term here, so it's 0, so you will get b equal to 3. And now what, use a and b, and then you get c is 7 by 2. Okay, so you have computed all these 6 coefficients in this case. So which means we have solved for the general solution, where we have used, so alpha 1, alpha 2 are the arbitrary constants, and rest is coming from the particular integral. So that's the general solution of the given ODE. Okay, so with this we have explained the method of undetermined coefficients in all possible, in all the cases of f that we can do, that is, which is exponential, polynomial, and trigonometric polynomial, right? I hope you go through this lecture more than once for you to understand better. I've given enough examples to kind of get across the idea and the various situations that can happen, like kind of roots which can be multiple and so on, and what to do in those cases. So I have kind of given at least one example in every possible situation. Okay, see you in the next lecture. Thanks a lot. Bye.